warm introduction, and thanks Fernando and Chris again for the invitation. It's great to see many familiar faces. So I actually gave a talk in Berkeley a few years ago in the Earth Science department, and for those from the Earth Science colleagues, I promise you this will be different, so you hopefully won't be bored. Today I'm going to talk about some of my group's recent work about enhancing neural networks representation accuracy. And I hope I can convince you that it is problematic that neural networks can suffer from representing multi-scale behaviors in the data, and that motivate our group to develop these algorithms to capture multi-scale behaviors in the using neural networks. Okay. So how many of you have seen this paper about emulating the global weather? So a few. Yeah, so this is I think what I consider as an example that get people seriously think about the use of neural network to approximate scientific data in the realm of climate and earth sciences. And what you're seeing here is a global wind velocity, and this is a neural network representation of the global wind field. And so if you compare that neural network representation with the training data, it's actually really hard to distinguish. How many of you think this one is neural network? So one of these is from neural network, one of these is from the classic the numerical weather prediction model. This one neural network. How many people think this one is from neural network? So actually, most of you are right. And this is from the AI-based weather prediction model, and this is the numerical weather prediction simulation. So generally, the one way you can tell is from the the large scale patterns is very well captured, but if you actually look at the fine scale details, you can see the neural network, the AI-based model missed lots of the texture that are there in the original numerical simulation. So this is the related to the so-called spectral bias, and one way to quantify this bias is to look at the energy spectrum of the wind field, for example. So here you look at the energy spectrum as a function of the total wave number, and the black line is the spectrum from the numerical simulation. The color lines are the spectrum from a few different AI-based neural network emulators. So there are a few different neural network emulators that all are very successful. But if you look at the comparison, so the spectrum of the AI-based emulator agrees well with the numerical simulation only at low wave number, but deviates at higher wave number. So this is consistent with the fact that the large scale pattern is captured, but the small scale details are misrepresented by the AI-based method. So and you see, so this is just a one time step of a prediction in the future. If you run a AI-based model for 10 days, you can see the deviation propagate from high wave number, small scale processes to low wave number. So at this time, even the large scale patterns start to become bad in the neural network emulator. So, one way to this phenomenon has been well acknowledged in the AI and science community. So I really like this 2019-2020 paper. Is one of the early paper that present this behavior, the so-called spectral bias. So spectral bias refer to neural networks' tendency to prioritize fitting signal with certain frequency range. So you can see on this very simple example, the blue line is a target signal, so it has low and high frequency. The green line is the neural network prediction. So in the beginning, it fits the low frequency component and take much longer iterations to capture the high frequency component. So this is a problem because in many problems, in weather and climate, we use neural network because of its property as a universal function approximator. However, in reality, if you deal with multi-scale problems, neural network most likely will miss the high frequency signals. Okay, so that motivate our group to design a architecture that can efficiently capture the high frequency signal. So this is today's outline. I'll first talk about a algorithm that we use to tackle this so-called spectral bias of the neural network. And then I'll talk about some applications using this new architecture to solve inverse problems, particularly the inverse problems that involves partial differential equations. Okay, so let's get started. And there are many experts of neural networks here, so I won't talk about the basics. But this is the first thing we have tried. We just use a neural network, simple neural network to fit a 1D function. So this is the output of the neural network, y-axis, the x-axis is the input of the neural network. We have a made-up target function as shown by the blue line. The red dashed line is a neural network prediction. So if you just do something like this, like a simple regression problem, you can get an error that's pretty small. So here the loss function decay over iterations, 10 to the minus 5, probably good enough for most applications. But the question we're curious about is why not lower, right? Like if the neural network is truly universal function approximator, you should be able to approximate down to arbitrary precision. So then, of course, we try increase the depth and increase the width of the neural network, just increase the number of parameters. That didn't really help much. So, pretty much this is about the 10 to the minus 5 is about the limit that we got. Then my postdoc, Yang Ji, who came up with this very smart idea, he basically freeze the original neural network and then look at the residuals. So here is the residual of the first neural network. And then use the second neural network to correct for that residual. And then by using this strategy, we can effectively get the error down by another 10 orders of magnitude. So here the block line is this multi-staging training strategy using a subsequent neural network to correct for the error of the previous one. The total number of parameters of the combined network is actually smaller because here the red line using one single network actually has more number of parameters compared to the two-stage approach. So the computational cost is actually not more, is similar to the
what is one single relative position of your computer when you do this? Because eventually
double precision, yeah. So
which is 10 to the minus how much?
Here is 10 to the minus. I'll show you a lot more that's even lower than this, which will be relevant to this discussion. But we're using 64-bit. Yeah. So without going into the detail, I want to just introduce this really nice analysis. I think Fourier analysis is a great tool to understand what the neural network is learning. And this is a very simple demonstration of why we could expect a spectral bias during the training procedure. So here, this is a simple one hidden layer neural network, right? In this case, we have X as input. Our output is U. So we're trying to learn to represent this function by learning the training parameters, the W's and the weights and biases. And in the loss function, we are trying to minimize the different distance between the neural network prediction versus the ground truth. So we have this mean square distance between the ground truth and the neural network prediction. And then now we're going to write everything in a Fourier space. So here the U hat is the representation of the neural network prediction in the Fourier space. Okay. So then you can actually rewrite this loss function in a Fourier space as the mean square distance between the target function and the neural network prediction. And then you can show that, so during the gradient descent, we're trying to minimize the loss function. We're trying to minimize the J by calculating how J evolve as you perturb the parameters data, right? To perturb these parameters, weight and biases. And it can be shown that this gradient in the gradient descent decay exponentially with K, where K is the frequency of the target function. So this is important because it shows that if the neural network, it would take this gradient will be very small for large k, large wave number, meaning that it will be it will take many number of iterations to learn the high frequency component, the large k component. Yes.
So is this true for other activation functions like sinusoidal, like siren?
Great question. So you can actually derive this for many different activation functions. It's true for many of the commonly used, like the ReLU. I've seen the form will be different, not exactly the same, but you still have the feature of like decay of the gradient for large k. That's I believe there's special activation function you can develop to get rid of this effect. But this is a simple explanation for why we could have a spectral bias. And a very simple way to fix it, and this is also commonly used in the literature, is to simply rescale the weight, because here you can use this exponential decay of the gradient of the loss function depend on the factor, the wave number divided by the weight of the neural network. And the weight of the neural network is a tuning parameter. So if we have a way to increase the weights of the neural network for larger frequency component, then we can activate the learning for large high frequency signal, right? Because we activate, we make sure this gradient is large again for the large high frequency component. And in terms of implementation, it's actually very easy to do. So what we did is simply in front of the neural network. So W is the neural network weights. We have a scaling factor. And for high frequency signal, we just have a high scaling factor. Okay. So this can be easily done with the so-called, there's Fourier features. That's also another implementation that's using similar ideas. So here is another independent idea. We talk about learning high frequency, but when the training error of the network is already very small, the learning generally become very slow, right? So here, the idea is to break down the signal to a superposition of several neural networks. So here, U0 is the first neural network, U1 is the second one, U2 is the third one. Epsilon 1 is some constant that's much smaller than the smaller than 1, and epsilon 2 is much smaller than 1, etc. So the general idea is that if we can use a superposition of neural network, each with different orders of magnitude, by adding together, we can approximate the desired function, because then instead of using one single neural network to capture all the details, you can use subsequent neural network to correct for the errors of the previous neural network. And again, there are also many different flavors. Sometimes in the machine learning community, people call this boosting. So using the error to correct for the signal that's not being captured by the previous training. The novelty of our multi-stage neural network is to combine the idea of this boosting as well as the frequency correction. So here is the demonstration, a numerical demonstration to show you how what this can achieve if you combine the two ideas. Again, this is another very simple 1D function. So the blue line is the target function. We know that. The red is the neural network prediction. Vertical axis is the output of the neural network. X-axis is the input. So it's a function. We're using it as to learn functions. And this is the residual of the single neural network, right? So the vertical axis is the magnitude of the distance between the ground truth and the first neural network prediction. The x-axis is the input, so it's just x here. And then you can see that the residual has the magnitude of 10 to the minus 4, so it's already pretty small. Usually it's probably good enough for you. But here we want to see how much smaller we can push the error down. So by using a second neural network to learn to capture this residual, we can see now the residual of the second neural network is even smaller. The residual of the second neural network now has the magnitude of 10 to the minus 8. And what's one thing that's interesting here is that the residual of the second neural network has not only smaller amplitude, it also has higher frequency. I actually don't know why that's the case, but we look at this residual of the second neural network in a.
Sorry, when it's just a amplified tables, convolution systems, and I further develop it, the amplitude of the high frequencies will be much smaller.
That's
so therefore
right.
It will only show in your higher error terms.
That's a great point. Although we have tried using a function that has a flat spectrum, and we still see similar effect. But that's a great intuition. Yes.
So, in learning the function, have you ever tried how this compare with adding the gradient and adding the hashing loss function? How does that help compare to a scale level?
You mean adding the how do you
the gradient and hashing of the function, because this is generally used in fitting force field in material science and chemistry. We care a lot about how the surface of the function, how smooth that is.
Yeah. I
would
using
multiscale neural network, we are approaching the different stage of the residual error. But how does this compare with adding the gradient hashing?
We have not added the gradient of the Hessian. So here, we have not played much with changing the optimization technique. But I think that will be complementary to this. So that can definitely be add on top of these. Yeah. So this the optimizer this here is just adding, and so it's very simple. Yeah. So if you look at this residue right now we want to use like a third neural network to capture it, because let's say you want to keep pushing the error down until you cannot push the error down further. So if you use a second another neural network to learn this, usually the challenge you will see is that you will struggle to learn high frequency function. But then because we have the kappa parameter to get a high frequency function to work, so you can essentially basically in Faku's work, we are rescaling both the y-axis and the x-axis to make it easier for a second neural network for a subsequent neural network to capture the residue. And the neural network with the information of the magnitude and the frequency now can capture the error quite well and then push the error even down to 10 to the minus 11. You can just keep doing this until reach the desirable error. And so one thing we notice is that as you add as you use the subsequent training scheme, the error goes down when you add one more network. The frequency of the error goes up, right? And you actually follow some scaling relationships here. So here the y-axis is the magnitude of the error. As you add more neural networks, you push the error down. But then the corresponding frequency of the error of the subsequent neural network also goes up. And it follows this 1/6 scaling, which we don't know where it comes from. We tried different functions, including the one with the like a uniform spectrum. We see pretty consistent behavior like that, this kind of scaling law. We changed the neural network size, the width, and the
each network to the same size at each scale, right? Meaning the total number of by size, I mean just the number of coefficients available.
Great question. We can you can use the same size, but you can actually use way less parameter for the first network, because the first network usually is learning some simple
course behavior.
Exactly.
The finer ones in your current experiments are all the same size?
It's all the same size. It's all the same size. Yeah, it's all the same size. But like it's relatively this scaling behavior is like not.
This is in 1D.
It's 1D. I will show 2D later.
Is alpha 6 also in 2D?
Let's see.
I
have to look it up. I will show an example of if the cost function is more complicated in the PDE case, it's not 1/6, it's 1/8. But for 2D, I have to look it up. I'll get back to you. It's a good question. Yeah. So in the beginning, I was like, who cares? I just thought it's really interesting. But if you have any ideas of like how to analyze and understand this, I'd love to talk to you about it. But then actually, this turns out to be quite important for some of the follow-up tasks I'm going to talk about in the PDE case. So here is like the observed, right, empirical model for this, the dominant frequency of the errors, how you scale with the magnitude of the error, right? So we have a power law where alpha approximately 6. So what this says is that you can, as we use this architecture to get very small error, we can not only get small error of the function itself, we can also get small error for the high derivatives of the function. So for example, let's say epsilon is the error of, that's the distance between the neural network prediction and the ground truth. So UG is the ground truth, is like this function. And then we can actually by plugging in this scaling law, you can estimate that the gradient of the error of the first derivative of the ground truth would scale with epsilon times the frequency. And you can derive that the nth derivatives of the ground truth will have error that scales with epsilon to the power of 1 minus n over alpha. This means that if you have larger alpha, you can actually capture the gradient, high order gradients. Okay. So then next I will show you a quick example of generalizing this idea to 2D fields. Here, my student Jenkins, she uses spectral solver to generate a numerical simulation to this 2D incompressible Navier-Stokes equation in a vorticity form. So I really like this example because it's very simple, but then it has, you look at the energy spectrum, it has like the wave number spans over towards magnitude. So it's a very simple multi-scale problem. And the first thing we want to check is, can we use this strategy to fit this kind of multi-scale with high accuracy? So this is just one snapshot. So this is a string function of that extracted from that numerical simulation. And then here we use a neural network to fit that string function, right? And then this error is capturing the distance between these two fields, the target versus the neural network. So the error is already pretty small, 10 to the minus 4-ish. So you could have stopped here, but we want to see how the error can be further reduced. So in order to design the next network, we have to know both the magnitude of the error and the frequency of the error. So we look at the error in the frequency space. So here, this is the two wave numbers in two dimensions. And you can see a dominant, the error actually has a dominant frequency. And if we look at the energy spectrum, so the black line is the target energy spectrum from the numerical simulation. The blue line is the neural network representation. So you can see the spectral bias, right? It captured the spectrum at low wave number, but then characterize the spectrum at high wave number, right?
Just a clarification question. Is exactly what the training data looks like? You feed randomly drawn X values and stream function at that particular point, and then you randomly drawn X.
We actually provide the entire, so we entire air it's uniform. We have uniform grid here. We provide the information of psi everywhere. So a randomly drawn example will be more challenging.
Okay, so you provide a uniform grid, you train it on those grid points, and then you ask it at the same grid points to.
That's right.
If it could memorize, get a perfect.
That's right. That's right.
I mean, would you, they talk about multiscale on Navier-Stokes equation on regulation grid. Which part is multiscale?
So mostly referring to, actually, if you want to use a better solver, you would use the adaptive grid solver. Here we were using simple uniform grid. But if you want to resolve the actual, like even higher wave number, you want to use some better adaptive grid solver. This is we generated this grid. We didn't really optimize the numerical solver at all. But the models will mostly just refer to, it mostly refer to this effect that the neural network can capture a frequency range, but then like doesn't capture the high.
Right. So the problem is not multiscale, but you're talking about neural network in multiscale one.
I think depending on what your definition of multiscale is. Yeah, like I think this tend to be an issue if you have, if you only have one orders of magnitude of frequency range, then it's not really a problem. But here you have two orders of magnitude. So I would call maybe like problems where you suffer from this kind of bias. That's the issue we're trying to address here.
No, I mean, it's terminology, I guess, and also in context of points, multi-scale issues, really give different physics components that all guide on different scales. And for all those spatial scales, then it's a multi-scale problem. Kind of like stiff equations, these kind of like equivalent of that. So here you don't have that situation.
I think this is not a good example. Let me show another more extreme example where the different scale has different physics. Yeah. This is a very simple benchmark example. So, but basically it's just to show you can actually use a neural network as a very good function approximator, right? Like you can push the error essentially down to machine precision of the double precision floating points. And you see the similar behavior when you add the complexity of the neural network by adding subsequent stages. The error have higher frequency, and as you add higher frequency, as you add subsequent neural network, you are also pushing the mismatch of the spectrum representation towards a higher length scale. So here is just a simple quick summary between if you have the same number of, if you allocate same number of total parameters and you allocate all that parameter to a regular one neural network training, this is usually what you would get. Like you misrepresent the high frequency component compared with the ground truth target. And if you look at the loss convergence, I love Fernando's question because here our first network actually is very small. We put more parameters into the later stages to capture the high frequency errors, and eventually you can go down to machine precision. And just to point out again, is not more computationally expensive because you are using less number of neural parameter compared to the single one. Yes.
So is it fair to say that your single neural net can represent the function well, just the optimizer just can't find that global optimum, or not really? Like it's just even if you can't magically find that global optimum, you get this.
I think it's a really important question because it's related to the Haitian question, right? If you have the same, let's say, given the number of neurons, maybe let's look at the red because the red curve has a lot of parameters, right? I would love to see an example where you can use advanced optimization methods to push the error down to machine precision. We haven't really tried playing around with the optimization method, so it's totally possible this was trapped in a local minimum. I don't know I don't have a good answer for you. I don't know if it's trapped because it doesn't have enough parameters or just because it's the optimizer.
Because what we're trying is you just initialize a random neural net and then get its response.
Yeah.
Use that as your ground truth. Now you know like this neural net can perfectly get that response. And then you try this again, just a different random initialization, run your atom and see what
if you try
versus.
Yeah, we can quantify uncertainty of these, right? This is very easy to do. But if you just use the random initialization, you wouldn't get down to machine precision. It would be very difficult without changing the optimization methods.
Yeah,
we can talk. Yeah. There should be non-unique ways to get accuracy. This is one way that we found very effective. Yes.
There's another place you could put this, which is a loss function, right?
Yeah.
It's possible that the fact that it's squared error is another way of getting at the same sort of question. Is it gradients or is it so because you're doing this batch-wise in a grid, you could put a loss on the kind of gradients right themselves. And then doing so incorporate the fact that you actually simultaneously want the high scales into the gradients themselves just by specifying that.
I think that will help. Okay. Yeah, if you change the the loss functions to penalize the learning high frequency. I think that would that actually we have tried something along the line with that, and then you actually push the alpha down to even larger values. So yeah, yes, there's a question with that.
Yeah, so just continuing on that. So do you think it's just like, you know, your inputs to the neural network just have a lot of energy, the frequency, is that kind of right? So like a lot of the energy, you know, it's analyzed energy, so there are a lot of low frequencies that's been learned out mostly in
That's right. It's relevant. Like when we minimize the mean square error, you're actually prioritizing learning of the biggest signal, which is the low frequency in this case.
Yeah, you could like whiten them out or something.
You could. I've seen a lot of people in the weather forecast community. They actually recognize that, and they like change the, they actually directly put the loss function in the spectrum domain. It can reduce the error, right? That's a good strategy. So a great person to talk to is Aditi. She wrote a paper about this. Like in the loss function, you directly put you penalize the loss, not just you're making sure the high frequency signal is taken care of. And one way to do that is to penalize the loss in the spectral domain. I think the coolest stuff is this is like a background warm up background material, and all these are like pretty old results. It was published 2 years ago, and the code is online. There are many variants of these. There are people trying to use this with different optimization methods. So I think that's lots of different variants of this idea now. But just to sum up here, we are not doing anything fancy. It's a simple regression problem. The major idea is that when you train a neural network, you take both the magnitude of the error as well as the frequency of the error. So both of them are equally important, and use those to get the subsequent error to be learned by the subsequent neural network. You can just then stack them together. Okay, so this is the application that I really want to show and discuss. So that was just to fit functions, right? Like as you use neural network to has a precise, accurate function approximator. We want to see if we can use it to represent PDE solutions and potentially discover new PDE solutions. So I think many people in the room who are familiar with the idea of physics-informed neural network. And just to recap, the neural network is used as a function approximator. Okay, so you have some solution as a function of input, and this is a representation of the solution to some equation. Okay, for example, you might have some gradient of some derivatives of the output with respect to the input, right? And because of neural network as it train through backpropagation, you already have you have the ability to calculate the gradient of the output with respect to the input. Exactly. So you take those in the training procedure. The additional thing you add is a way to put this equation into the loss function. So you would evaluate the neural network output in the equation. So for example, you would take the second derivatives. If this is the equation form, you will substitute the neural network result into the equation. And then if the neural network result is perfect, let's say you have an analytical solution, then you should have 0 residue, right? But it's not going to be 0. There's going to be a numerical error. So in the loss function now, in addition to some data, you also have this. You directly put this equation residue into the loss function. So you want it to be as small as possible. Okay. So in the rest of the time, I want to show you 2 examples I'm very excited about. The first one relates to finding singularities in fluids, and it's one of the problem where we know the PDE, we know the equation is given, but there's no solution. It's really hard to solve those PDEs. And in the second example is related to inversion in geophysics, where we have lots of observations, but we have partially unknown physics. So I'll talk about both, and I start with the first one. And so this was broadly motivated by my my very first conversation with a professor when I was in Princeton about the Millennium Prize problem. The Millennium Prize problem is about the property of the Navier-Stokes equation. And I really love the Navier-Stokes equation. It's my favorite equation in the world just because, you know, it's so universal, right? Like it's so generalizable. you can use it to describe things that happens, you know, like in this cup, like the water flow. You can use it to describe Earth's atmosphere, right? Like, so it's so incredible just how, and it's not that complicated. If you look at the terms, you know, you can write it down on a piece of paper, but it's incredible. And very powerful. However, if you ask a mathematician, there's actually many fundamental questions about this equation that we don't quite understand. For example, one of the Millennium Prize problem is whether the Navier-Stokes equation always exists a unique and smooth, meaning infinitely differentiable solution at any times. So one pathway that many people try to tackle this problem is to find a counterexample of the statement. So if you can, for example, if you can find a solution that satisfies the Navier-Stokes equation, but then it blows up at a finite time, then that would be a counterexample. So here we want to see if we can use a highly precise neural network to find the blowout solution, because, you know, as we show that the neural network can be highly precise, and we know the equation, we know the PDE, so it's really an optimization, right, problem. We want to find a solution that is precise and satisfying Navier-Stokes equation, but also has blowout behavior. And I should mention Navier-Stokes is actually really, really hard. I don't know if we'll ever be able to solve it, but we solved a simpler problem that used the for the Euler's equation. So Euler's equation is the Navier-Stokes equation without the viscous term, and this was published in PRL 2 years ago. And just to introduce what we are actually trying to do, here's a very simple example, a benchmark example. When I talk about singularities, right, we're talking about some quantities that become infinitely large. So for example, you can actually reproduce singularity with such a simple, very simple implicit Burger's equation. So if you solve this equation, you can actually get shock formation at a finite time. So this is the example, the solution U as a function of X evolving with time. If you look at the gradient, it will become infinite at the time when shock forms. So it's really, the space domain is actually not a good coordinate to describe this process, right? So in this problem, we're going to work in a different domain called the self-similar domain. The self-similar domain evolves with time. So the self-similar domain is shown by this red box. So basically, zoom into the formation of the singularity. So if you look at the solution in a self-similar domain, you can see that the blue line is the solution after the transformation. You actually, although you have a really steep slope in the original domain, but it actually can be described by a very, very smooth solution profile in the self-similar domain. So the first thing we're going to do is to transform everything into a self-similar domain where things are easier to represent. So we will apply this kind of self-similar transformation. All we do is to rewrite the original problem in terms of capital U and in terms of a new coordinate that evolve with space and time. Okay, so this parameter here is the description of the x-axis here, and one unknown parameter. So we actually don't quite know how to do the transformation. So in this problem, we have actually two goals. Not only do we want to find the solution profile, we also want to find the parameter that tells us how quickly we have to zoom into the singularity in order to capture the results. So therefore, this is actually an inverse problem, right? If you this is the equation we are trying to solve. After plugging the self-similar answer to the original equation, you have a simple ODE that we are trying to solve. If you know the lambda, this is actually a trivial numerics problem, right? You can solve it just get a solution. But in this problem, we actually do not know lambda. Right? So we are trying to get the capital U profile as well as the transformation that give us this self-similar solution. And this is to show you that it works pretty well. So here, as you train a neural network, it's going to find the solution, and as well as the lambda value. And in this problem, we have the exact solution, so we can check that it's doing the right thing. And if we use the multi-staging technique, we can push the error essentially down to machine precision. So after the first stage, the only here again we don't have data, right? We are not using the numerical solution to learn the solution. We are only using the PDE in the cost function to find the right solution. So the only thing we can use to understand the solution quality is the residue, the equation, the PDE residue, right? And the PDE residue, if it's 0, then the solution is exactly correct. So we want it to be very small. Right.
So again, precisely, can you just say exactly what the training data is? Is it a grid of y and time in U?
So the training data is a boundary condition for U. So it's a we provide like we know the U value here. That's the only thing we know. That's the only training data. The rest of the solution is predicted because of the PDE.
The loss function. You encoded the PDE in the loss.
Yeah, the loss function has the equation. So none of these is given other than the boundary condition. So it's like a numerical, it's like a PDE solver. You can make prediction because of the equation. Yeah. And then you can look at the PDE residue to see how accurate the solution as a way to quantify how accurate the PDE solution is. So with a 3-stage neural network, we can get the PDE residue down to 10 to the minus 14. And then in this case, because we have the ground truth solution, we can compare this prediction with the ground truth. The ground truth is not being seen by the neural network, but we can see the actual error. It's close to machine precision of the double precision floating point. So that was a very simple example, right? What we want to solve is the Euler's equation. So again, this is a 3-dimensional incompressible Euler's equation. And the major open question is whether there exists smooth finite energy initial condition that can lead to a solution that will blow up at a finite time. And classically, there has been excellent computer fluid dynamics developing numerical solvers to solve this equation directly in a space-time domain. And in their simulation, they do see at some finite time the vorticity increase a lot, and that suggests that there could be a singularity formation. Here we want to see if we can leverage the neural network's expressiveness to represent highly accurate solution that can lead to blow up at a finite time. So just to show you what we are trying to do, here the cross-sectional view of the fluid flow. In this case, there's an image. We consider an imaginary cylinder that follows the scenario considered by Lu and Tao in his numerical simulation. And in his numerical simulation, he see like flow going downwards and upwards, and this is the point where he see singularity formation. So we use the same scenario, and then
the quantum that diverges vorticity with energy constant. It
vorticity.
still respects energy conservation, but vorticity is diverging.
That's right. That's true. Okay. So that's right. Energy constant, but the vorticity blow up. So we again actually, if you use a neural network approach to solve this in the original time space domain, it will be extremely difficult because you just cannot represent growing vorticity. That will be really hard. But so we represent everything in a self-similar domain, like what we showed earlier time with a simpler system. So the first thing we have to do is to transform a coordinate into a self-similar domain. And then the original equation now become a set of 5 different equations. So this is the neural network architecture. Now the neural network is used to represent 5 different solution profile as a function of the input. The input is now the transform coordinate called the self-similar coordinate. And these are the 5 equations that in the self-similar coordinate that we're trying to solve. again, we are interested in not only the solution profile, but also the parameter that define the transformation, which is this lambda parameter. There's a lot of details that I won't talk about here, but I'll tell you the essence of the approach. So some of the things that we can add to this kind of neuron PDE solver is you can add knowledge such as symmetry. You can define the solution as in this way, such that you impose symmetry as a hard constraint. You can we have knowledge about the smoothness of the solution, so you can penalize the gradient of your solution in some locations. In a cost function, we can in this problem we know that because we have boundary conditions at the far field that's like around 10 to the power of 12, so it's really far from the center. But the boundary condition matters. So in this case, we have simple coordinate transformation, use this hyperbolic sine function to map a very large domain to a finite domain. So the neural network is solving everything in the finite domain, but it maps to the original problem in the very large domain. So, after 3 years of work, we got a neural network that was able to minimize the error, both the equation loss and as well as the loss that correspond to those those conditions that I just mentioned. And you can so here we have these are the neural network profiles, 5 different profiles. So after training for about 10 hours of GPU time, this neural network was able to find a set of self-similar blow-up profile, and we can evaluate how accurate it is by substituting it back into the equation and look at the magnitude of the PDE residual. So in this case, it's about 10 to the minus 4. And this was actually a first example where the neural network found a set of numerical profile that hasn't been previously found with other numerical methods. So, and we show this to our math colleague, and they say, sure, this is great, but in order to generate a mathematical proof on the numerical profile, our residue has to be down to 10 to the minus 8. And we were like, okay, then we will use our the multi-stage neural network. So here is the first stage of the neural network, and then with the second stage, we were able to push the residual by another 5 orders of magnitude. Again, I totally I love the idea of also using advanced optimization technique, changing loss function. I think those will all help to push the error lower. And so this is we're trying to write this up. And there's actually a subsequent work after our PIO paper that use a more classical numerical methods to find a similar self-similar profile to the same equation. And in that paper, it's actually admirable. I think the two community can really collaborate. It's not necessarily competing, right? Like you can use a neural network, find something, and that can inspire a new design of the classical numerics and then validate the result. So in this case, they found like lambda value that's up to 7 decimal places, same as our results. And they were actually they generate a mathematical proofs on top of their numerical solution. So yeah, and so that was the first part about finding singularity. How much time do we have? Okay, so I'll just quickly run through the and maybe 2 more minutes. Is that okay? Yeah. And I think for this crowd, right? Like, okay, I'll see you later. In many problems, you probably don't need really accurate solution, right? You probably because your PDE might not be correct either. So in many problems, you probably don't need very accurate representation. However, in many problems, you could have like different types of multiscale problems. For example, you still have an issue related to the spectral bias. So I will quickly talk about this. What goes into this second application. So in this application, we have lots of data, but we actually don't know the physics that well. So we actually don't trust the PDEs. And just to show you, this another my favorite application. This is the I sheets. if you look at ice sheets, right, you thought it's a solid. Yeah, sapphire energy is flowing just like a fluid, right? And in order to make a prediction like this, like a flowing ice sheets, we have to know the viscosity structure. But this key parameter related to the viscosity is something we actually cannot directly measure. This is the essence of this work is can we use the data to help us find a better viscosity model such that we can make a forward prediction. And just to show you, in this problem, we have some PDEs and we have observations of the some of the quantities, the velocity, and the thickness here. So really the only thing we do not know is the viscosity field. So we just have one unknown. And then using the same approach, we actually, the code is strikingly similar to what we use for the Euler blowup. Using the same code, we inject the physics equation, we inject the data, we can find a viscosity field like this. So again, this is a prediction of the viscosity field. We do not have any observations, so there's no training data for viscosity. This is predicted purely based on the Gaussian equation. And of course, we could evaluate how precise it is by substituting this back into the equation. And just to compare, if you use the uniform discretized grid to represent this with the same accuracy, you would use 2300K parameters to represent the same field with the same accuracy. With the neural network, because we can tune a lot of we can optimize it to use a more efficient parameter, more parameter efficient way to represent it using a neural network. You're only using 40K parameters. So just want to see, once we get a viscosity, you can actually test hypotheses. For example, one of the hypotheses, and this in fact going to the ice sheet model, traditional ice sheet model, they always assume that the strain rate increase with stress as a power law. So here, by using the viscosity, we can calculate the stress, and then we can actually look at whether this power law hypothesis is correct. And we see there are places where it's correct, but there are also places where power law is actually not satisfied. Importantly, the power law exponent, usually in ice sheet model, is assumed to be 3, and here we see a range of power law exponent between 1 and 4. So if I think about what's the essence of this project that makes it work eventually, I think it's a separation of the physics that we are confident about versus the physics that we are not unsure about, right? Because not all the physics are good, right? Like we have some PDEs, like the momentum balance we believe is correct. So we still keep this in a loss function. But like the viscosity model, the power law model, we're less certain about. There's actually no direct observation that suggested. So we leave this as the component to be learned by a neural network. And I think I will just stop here and by saying, all the work I talked about was the Don postdoc. He's tremendous and really smart applied mathematician, broadly interested in climate problems, also on the job market. So good to consider. And I'll stop here and take questions.
You began the talk by introducing the spectral error problem, spectral bias problem in the Ching-Yao model. Do you think you can fix that with a multi-stage approach, or
yeah,
that much of a direct path forward?
We could definitely fix that. It's in a turbulence example that if you look at the high frequency example, high frequency component, in a simple vanilla network, you would not be able to capture it. Yeah.
But in your 2D barometric turbulence, I think if I understood you right, you weren't doing prognostic, right? You were just learning. You were only looking within the training data.
Oh, I see your question. You're talking about like if we have a PDE and then we have no training data, the spectral bias.
Well, or if you have training data, but then you forecast out a sample. Does the multi-stage method fix the spectral bias problem in a way that could be applied to these AI models?
I believe so. I believe so. But so far, all our demonstration is for simpler problems. Well, we have a demonstration for the ice sheet as well, like one single net where you just cannot capture all those spatial variation. But for those the AI prediction in the future, that those I think it's doable, but we haven't done it yet. Yeah.
So we also did comparing like the LBF and Adam, and we also see very similar for Adam for like conventional training other like the images of Adam predicted as linear policy. Then training any RPD data it always shows cycles, quite periodic cycles. So we're wondering why jumps come to stop and like reduce learning rate somehow. And I think most things that we should increase the efficiency block. I think my question is, do you understand why there's a very periodic jump for Adam for training PD?
So that's it. I think we do see that as well. Like with the Adam, we see lots of jumps. I actually I don't know. I think there are probably people who understand optimization better here who can answer that question. But you're talking about the loss, right? I think here is a good example. Like here like Adam is like lots of peaks and LBGS is pretty small. I don't know. I think we see this a lot as well.
And this is pretty unique to PDEs. And if we train other just images or language, I don't know, just